Good morning, ladies and gentlemen, or evening, whenever you might be enjoying this new video. First video here of our latest chapter, Chapter 3. We finally get to be introduced to the concept of vectors. So, Chapter 2, we looked at motion in one dimension. Here in Chapter 3, we're going to be looking at motion in two dimensions, okay? And we're going to be utilizing vectors to help us accomplish that. Now, in today's discussion video, we're going to just take a quick gander at what a vector is, some of their properties. Most likely, you'll probably have the PDF version of the notes before you get the hard copies, and that's okay. Today's discussion is going to be somewhat short because we're just going to get an introduction today, and then eventually we're going to really get involved in vectors and motion in two dimension, okay? Now, what our goal in today's discussion is to distinguish between what's called a scalar and a vector, okay? Nothing real too crazy about that. We're going to look at adding and subtracting vectors by using the graphical method. And then we're going to multiply and divide vectors by scalars. Now, we're actually going to do that. We're going to discuss what happens. We're going to do some work a little bit later on when it comes to this stuff, back when we actually get into full discussion mode after our Chapter 2 test. But I just wanted to get us a little head start on some of this information so we can try to keep up on pace with getting some material to you. So, what is a scalar and what is a vector? Well, a scalar is a physical quantity that has magnitude but no direction. Speed, volume, the number of pages in your textbook, those all have magnitudes or a quantity, but we do not use the idea of direction to further describe the motion. A vector, on the other hand, is a physical quantity that has both magnitude and direction. So displacement, velocity, acceleration, all terms that you should know by now. They all have magnitudes as well as direction. So when you're solving for a vector, make sure you include the direction. And you will notice that some of these directions that we're going to be discussing when it comes to vectors are going to be somewhat specific. Okay, so in your book and in our notes, you're going to notice that scalar quantities are going to be in italics and vectors will be bold-faced. Okay, that way we can differentiate between what we're looking at. Anyway, when we are talking about vectors and displacement, one of the things we're going to be looking at is a term called resultant vector. And this is really just a sum of two or more vectors that were used. So basically, your overall displacement from your starting point. And we can add them graphically. And that's kind of what we're going to be doing today. And you'll be doing for part of your homework. So a student walks from his house to his friend's house. Okay, so right here, this is the student, and they are going to walk to their friend's house. This is the first vector, vector A. You notice how we represent vectors with arrows, okay? Then from his school or his friend's house, they walk to school. So vector B here is going to represent their second displacement, okay, their second direction of travel. And what we get is what right here, C, the resultant vector. How far did the first student, how far is he away from his starting point? Yeah, he walked all the way over here first to his friend's house, then from his friend's house to the school. But the resultant vector here would simply just how far away is he from his original starting point, his house. That is how we help determine, graphically speaking, displacement, really. Okay. Vectors can be moved parallel to themselves in a diagram. Vectors are unique, and I've mentioned this once or twice before this year, where vectors are unique in the fact that you can move them around. You can take multiple pathways. but oftentimes the resultant vector or your displacement never changes. And so when we do graphical solutions for vectors, there's some things we have to remember when we do them, okay? When we are doing vector drawing, doing it graphically, we always draw our first vector first, and then our next vector, we are going to have the tail end of the arrow touching the tip of the previous vector. As long as we don't change size in vectors, we can put these almost in any direction. I'm going to show you an example here in just a second. And so we can then draw the resultant vector from the tail of the first vector to the tip of the last vector. So I've got this little graph. I have made some slight modifications to this since I printed them out. So if when you get these notes, you're going to see that they're going to be a little out of order, only by like a slide. I didn't take anything out, just kind of switched around the order. So if we look at this, let's say that this person first walks to the right. This is going to be not the best, okay? And that's our first vector, okay? We then walk north, let's say. So my second vector, I'm going to start from the tip of the previous arrow head, I guess you will, and then my stopping point, let's say, is right there. That's where I ended my walk. My resultant vector is going to be this dashed line. And when you're in class, I'll try to do this a little better. But this is our resultant vector. These two vectors, or vectors of motion, these two parts came together for my resultant vector. Okay? They're not always going to be the nicest and cleanest 90-degree angles, okay? Where we could use Pythagorean's theorem to help us solve for this resultant vector. But there are other ways that we can solve it as well. We're going to see it today. One's the old school method, as I like to mention. But that's our resultant vector. But watch. We saw in the previous slide that I can move these parallel. Okay, so I'm going to take this. We can move either one. I'm going to take, let's say, this vertical one. Okay, I'm not going to change the size or magnitude of it. Okay. Oh, that's not real good, but you know what? I did my best. Okay. So I just moved this vector over to the left. And so 1, 2, 3, 4, 5, 6. Okay. So that's not what I wanted to do. Come on, Dorfler. I said parallel. Okay, I just kept it in the same location. Okay. Anyway, I want to move it parallel to the original one here. Okay. I apologize for my driving. I can't even speak today, folks. My drawing. See, and again, I get my resultant vector. The displacement is going to be the same. No matter which direction I first started going, either north or east, my overall displacement is the same. I still ended up at the same location, and it's still going to be the same length. That's one of the properties we have to keep in mind when you are working with vectors, okay? You need to know that there could be more than one right way to state an answer or to solve an answer when it comes to vectors and two-dimension motion. As long as you indicate it using the proper direction, and here in just a minute, you're going to see the proper angle. So it's okay. It's okay. We're going to do a lot of practice this chapter with this stuff. So let's erase my wonderful vector drawings here. All right. All right. Now, as I tried to do my best to demonstrate to you on the previous slide by my drawing, that we can add them in any order. Okay, we can go about this in any order. And this fact right here is one of the concepts that we're going to use for one of our first activities regarding vectors. I love this activity. We're going to be doing scavenger hunts that we can only describe locations or directions using vector values. Okay, it's pretty fun because it doesn't matter what order you put them in, you'll still get to the same displacement. If we ever have to subtract a vector, you simply just add the opposite value. Okay, so if you had a vector that went 3 kilometers east, to subtract it, you just say 3 kilometers west or negative 3 kilometers. When you multiply or divide vectors by scalars, we still get vectors. Okay, so if you multiply a vector of 2 kilometers to the right by 2, you get 4 kilometers. Okay, so just 2 being a scalar, again, it's a number that doesn't have a direction, we'll still end up with vectors. Okay, so I have a little practice here that I'm going to try to do here on my dry erase board. We're going to see how well it works. I am going to be utilizing a protractor and a meter stick. Okay, this should go well. Usually I do this up on the board. It's a little easier that way, but we don't have that option at this time. So we have a small plane. It's taking off from a runway and first travels a distance of 200 meters. It lifts off and travels 110 meters at an angle of 35.0 degrees above the horizontal. What is its displacement from its starting point? So if you listen to that question, there's a lot going on. You got distances, you got angles, you have a thing that says above the horizontal. So what does that mean? Well, really just giving you instructions on how to draw this, okay? Now, I obviously don't have 200 meters or even 110 meters worth of space here, but what I could do is I can make a scale version of this motion, okay? And so I've got millimeters on this meter stick along with centimeters, but centimeters still wouldn't even work out, okay? I don't have 2 meters of dry erase board. So I'm going to use millimeters. And so that means that I can draw as best I can on my desk. I'm going to draw, and I'm going to assume, again, you can make a lot of assumptions. Okay, make a lot of assumptions when we're doing physics here, that we're just going to be taking off to the right. Okay, it says we traveled, wrong slide. It says we traveled 200 meters before we took off. So 200 meters to millimeters, what's that? It's going to be 20, right? Boy, I don't know if I have enough room on the dry erase board. So I'm just going to start from 20 and draw a line to 40. Okay? This is my 200 meters. And it says that once it reached the 200 meters, it took off for a total length of 110 meters before it made other adjustments, but we're not concerned about those. It also flew at an angle of 35 degrees above the horizontal. So, okay, let's determine our angle here. So, when it says above the horizontal, we can think of this first line as the horizontal. Okay, it's the viewpoint that is off the horizon. Okay, and so what I'm simply going to do is I'm going to put my protractor down, and I'm going to measure and find out where 35 is. Okay, 35 degrees from that angle. Also, if you have a protractor at home or in your book bag, bring it. Okay, I'm gonna darken this just a little bit. There we go. All right, so here's my angle. So now it says that he goes at 110 meters at this particular angle. So 110 meters, that is 11.1 millimeters. So I'm going to start here and go to, keeping with that angle, the best 110 degrees or 110 meters that I can. And this is 35 degrees right there. Okay? And this dashed line will say it's the horizon, okay? So 35 degrees above the horizontal. And now we need to figure out, well, first thing is when I was doing this, you got to draw arrows to indicate vectors, okay? So again, my first vector meets up with my second vector. The tail of my second vector touches the tip of the arrowhead on the first vector, okay? So now, if I can get this situated correctly, I'm going to go from the point at which the plane started to the very end of the second vector, which is what we're concentrating on. And I measure, again, using the same scale, okay? I have 60, I started at 60 degrees, 60 here, and it ends at 90. So, oh, that was terrible. So the resultant vector, RV, will be 300 meters. So after this vector and that vector, given it that angle, the plane has traveled 300 meters, or I should say its displacement is 300 meters from its original location. Now, it's obviously traveled a little more. If we think it's traveled 200 and 110, it's traveled more than 300, but because it took off at an angle and its relationship between where it started and where it ended, it's only traveled 300 meters. So that's how we graphically do it. Now, when you get in here, we're going to do some more. Don't worry. It's very difficult to see it on a little camera with a miniature dry erase board here. So we'll do it, but I still want to see how you can do this on your own, how you could think through this. So at some point in the near future, after you've watched this video, you will be given an assignment, okay, where you will have to basically take what we've discussed in this first section and work through it. Now, it's only like 4 or 5 questions I'm going to assign, okay, but I just want to see. We will do more practice with this. Don't you worry, okay? But that's it for this video. And I'm going to go ahead and stop it, and I will be getting this ready for finalization. I will talk to all of you later on. Bye-bye.